All right, so welcome everybody, and it's my great pleasure to introduce Matt McQuinn. He's a theoretical cosmologist who works at the University of Washington and is taking advantage of that 1 week in the year where the difference between Washington and the UK is only 7 hours rather than 8. So Matt did his PhD at Harvard University. And was subsequently first an Einstein Fellow and then a Hubble Fellow, and then moved on to the University of Washington, where he's been ever since, teaching the next generation of scientists all about cosmology. So he works on the large-scale structure, reionization, radio signals, and I am terribly intrigued by his abstract that ends with the fact that he may tell us something that is only a little bit crazy. So I'm just gonna go and let him talk about this.
Thanks so much. It's a total pleasure to be in Cambridge virtually. Unfortunately, I guess I do have a little bit of bad news regarding the abstract, which is that project that when I gave the abstract a couple months ago, like I was pretty sure it would be done in time, and it is not. But I am so excited about it, so unfortunately I can't present on it. But if you know what I'm talking about, just look out for that paper. So I love interruptions during my talks. I know that's a little bit difficult over Zoom, but I'm happy if you want to shout something out, or if something's unclear, please just let me know. Today I'm going to tell you about kind of an adventure that a bit of a diversion from kind of the standard research program that I've been pursuing, that happened over about a year, ending maybe a couple months into the pandemic, with a Nature paper that we'll discuss. It has to do with fast radio bursts. Most of you probably know what fast radio bursts are by now, but if you don't, they're this really bright millisecond radio transient. They were rediscovered by in a now famous paper by Thornton et al. In 2013. And the reason I say rediscovered is that there was an earlier event that had been reported that's called the Lorimer burst in 2007 that shares the broad characteristics of all FRBs, which is they have a pulse that is very bright, that's and lasts about a millisecond. Very bright means larger than a Jansky, and this is once you de-disperse. If you don't know what that means, don't worry. And if you look at the arrival times of different frequencies, then the arrival times sweep in frequencies. So the higher frequencies arrive earlier, and the lower frequencies later. And this is because the radiation is traveling through a plasma with electrons. And the group velocity is less than the speed of light, and frequency dependent. And so from this sweep, you can read off what the electron column is to the burst. And the reason people were excited when these were first starting to be discovered is that these are out of the plane of the galaxy, and yet the columns were really high. The electron columns were, if they were coming from the intergalactic medium, you would have to put these bursts at about redshift 1 for this Thornton et al. Sample, which corresponds to an electron column in units that we're going to use a lot, of parsec centimeter cubed, of 1,000. And I'm also going to switch over kind of to the radio parlance of calling the electron column the dispersion measure. And I'm going to not, there's some subtleties, the fact that things are redshifting, and so it's not exactly a redshift a column that I'm going to ignore. Okay, so people were excited. We had this potentially extragalactic source, extragalactic millisecond radio transient. And so I also got excited once I learned about these FRBs. And so a few months after, I wrote a paper about the potential for using these FRBs to probe diffuse gas. And I'm going to talk about this paper eventually in this talk. But at the time, it felt a bit like a pie in the sky paper, because we really didn't know a lot about FRBs, and a lot had to go right for this proposal to work. And so at the time, 2014, we weren't sure that they were extraterrestrial, and in fact there was a similar transient, similar in that it had this similar sweep in dispersion, sweep in arrival times that was known to be in the near field. All of these at the time had been detected with the Parkes telescope in Australia, and there was a similar transient that was seen in multiple beams, and so in the near field, and it was conjectured that maybe the FRBs were just part of the same class, but maybe a little bit further away, and that would be bad. In addition, not only would they have to be extraterrestrial, they would have to be extragalactic, and we would have to start, for the science that I'm going to discuss, localizing them to individual galaxies, and that requires being able to detect them with an interferometer, and in particular, you need to be able to isolate them to an arcsecond or so, localize them to an arcsecond or so, in order to say that it's in one galaxy and not another galaxy. And then for this science, also the host galaxy contribution to this electron column, the dispersion measure, it's easier. The science is easier the smaller this is. Okay, so I wrote this paper, and then I turned to other projects. But this was at the same time, this was a really exciting field, and things kept advancing. And so I kept watching this field. And in 2015, this terrestrial source that might have been associated with FRBs people figured out what it was. It turned out to be opening microwave ovens while they're running. And in a hilarious paper where some of the sleuthing involved noting that these events clustered around lunchtime, it was shown that the FRBs are something different. So now we know that they're not from this Earth. And then in 2017, the most famous FRB, which is called the repeater, which had been discovered by Arecibo a couple of years earlier, was localized with an interferometer to be in a redshift 0.2 galaxy. So in 2017, we knew at least one of these FRBs was extragalactic. And then the reason things got exciting the last couple of years is that we started localizing a lot more, and not even just repeating FRBs. And in fact, many of the papers I'm going to discuss are the ones that generate this current sample of much of this current sample of 10. So now we have about 10 FRBs that are localized to galaxies. And then I think an implication of this talk is, at the very least, the host galaxy contribution to the dispersion, which harbors the science that I'm going to discuss, would inhibit the science that I'm going to discuss, is at least not horrible. Okay, this is my only slide on what FRBs are. This is largely immaterial to the science in this talk, but let me just say a little bit. So there are a lot of them, and this is why we think we're going to get many more FRBs in the future. Like we're kind of on the exponential part of the number of FRB curve with time. So every year we're getting more and more. And the kind of the estimates are that there are 10,000 on the sky per day. This is likely too many to be from a single cataclysmic event. So whatever they are, likely is something that emits multiple FRBs over its lifetime. There are several arguments for neutron star origin, and the most simple being just the millisecond timescales and the fact that they're coherent emission and survive. And if of all hypotheses for what they are, the hypothesis that seems to be winning as of 6 months ago is that they're from magnetars. The reason for this is that there was a detection of a radio burst from our galaxy that it looked very similar to a dim FRB. So it would have been 10,000 times less bright than or less luminous than the extragalactic FRBs that we know. But other than that, it looked like an FRB from a galactic magnetar. So much of the community now thinks that these are coming from magnetars. And even before this event, there was a lot of thought that might be the case. However, I think another thing that we know is that it's very likely that they're different, maybe younger and maybe in some other ways exotic to the magnetars in our galaxy. Okay, so this talk is not on what FRBs are. It's on using FRBs to explore intervening gas, as their electromagnetic properties are sensitive to the cosmic plasma. And so we're gonna give a little context. So now we're gonna go in a different direction for a few minutes, and we're gonna talk about the baryons in the universe, the low redshift universe. Any questions or comments? Okay. All right. So we don't have a great accounting for where the baryons are in the universe. This is the so-called missing baryon problem at redshift 0, and so about 5% of the baryons, and even here they're order 1 error are in galaxies, where we can see as stars or gas in galaxies. 5% we can see in hot halos, like in clusters of galaxies, because this gas emits in the X-ray. And then everything else is either not hot enough to emit substantially in the X-ray, or just too low density to see an emission. And in particular, I'll remind you that the redshift 0, there's about less than an atom per cubic meter. So the universe is very low density. And so our best way of finding the baryons is with absorption line spectroscopy. And then it turns out that the atoms that are the best at holding on to electrons are metals. And so then you're left with interpreting things like oxygen, 5 times ionized oxygen or 6 times ionized oxygen, and then trying to infer what that means for where everything else is, and it's really hard. So there's a lot of uncertainty. It's really hard to figure out where everything else is. But you might say, okay, maybe I don't know where it is, or maybe I can't see it directly, but I have a good enough model. This is diffuse gas that's relatively far from galaxies. So maybe it's just something that it's hard to see, but it's not super interesting. And I would argue that is not the case. And so the argument goes as follows: if you go to redshift 0 and you calculate, well, I guess we don't have to go to redshift 0. At redshift 0, you calculate the amount of mass in dark matter halos that resides in 10 to the 10 to 10 to the 14 solar mass halos. So these are halos that are massive enough to be able to pull in their gas from the intergalactic medium, but also at associated with temperatures that is able to cool in probably a shorter time than the age of the universe. Then the amount of mass in those halos is about 40% of the universe. And so your picture for the universe might be like, if you just had to guess, that 40% of the baryons should be in stars at the centers of these halos, and this is not the case. Only 5% of the baryons are in stars, so star formation has been really inefficient. And so the question is, where did the rest go? So somehow feedback from stars and AGN have redistributed these the other baryons, the other part, the 35% of this 40%. And so then we can't see them very well, like the bulk of them. And so then our way of addressing where they've been redistributed is with cosmological hydrodynamic simulations of galaxies. And so then you can ask, do these simulations all give the same prediction for where the baryons around these halos have been redistributed? And the answer is no. So this is a compilation that was done for the cosmic microwave background, which leads to the curve shapes being slightly confusing for reasons that are explained. But this is the gas surface density. You should think of it as the gas surface density as a function of impact parameter for 10 to the 13 solar mass halos. This is an order of magnitude more massive than the Milky Way, but similar conclusions hold for Milky Way, maybe even more discrepant. The different curves are different of these state-of-the-art simulations. And the thing that and this is the virial radius of these halos. And the thing that you should note is that these different curves are substantially different, even out to a few virial radii. And so how these simulations are putting in feedback from stars and AGN is resulting in different profiles for gas. So we have at some level, like at redshift 0, there's kind of an order 1 like problem on the cosmological scales, like that, where the baryons around these around galactic size halos, we don't have a great model for, and our best models are making different predictions. Okay. But I know that some of you are cosmologists, and you might not care much about galaxy formation simulations or galaxy formation. And so I'm just going to tell you that, and this you probably know, that this is becoming an issue for cosmology. If we're trying to do percent level cosmology, and we've really invested a lot in weak lensing, and what we're finding is that the kind of one of the dominant uncertainties and what's inhibiting us from using as small scales in for example, the correlation function of shear correlation function is that we don't have a great understanding of where the baryons are. We don't have a great model for where the baryons are, and so this is also important for cosmology. Okay, so that was the diversion. We're going back to FRBs. Are there any questions? What is shown here is the primary instrument that we're going to be using data from, which is ASKAP in Western Australia. Okay, so I'm going to point out that galaxy halos are big. So a given FRB sightline that's going a cosmological distance through the universe goes through many galaxy halos. Like given this is the Hubble Deep Field, it doesn't given if I just take a random point here, it's likely not going through a galaxy. But let's say we go to this galaxy, its dark matter halo is something like 50 times larger than its half-light radius. So if I just start drawing on dark matter halos, then maybe its dark matter halo looks like this. And then maybe we go to this elliptical galaxy, which maybe is a little bit more massive, and I draw on its dark matter halo, maybe it looks like this. And then I can keep going until I get bored. And the upshot is, if I'm shooting like a sight line through the universe, it's going through many of the dark matter halos within their virial radius. And so the FRBs are in a sense, they're and in ways that we'll discuss are probing this gas. Okay, and the way here we're going to discuss how. And so there are 3 plasma phenomena that FRBs that we can measure from the electromagnetic properties of FRBs. So the first is Faraday rotation, and in particular, what we measure is the rotation measure, which is that if you have a polarized source and you have a magnetic field and electrons, then the magnetic field along the line of sight, then the angle of polarization angle will rotate, and in a frequency dependent manner that you can distinguish. And this gives you an integral over the sight line of the electron density times the parallel magnetic field. There's scattering. So if whatever is between your FRB and your telescope has a lot of structure, then there can be multipath propagation, because you can think of it as there's a lot of extrema in phase on this structure that look like images to my telescope. And so the multipath propagation, different paths take different amounts of time to get to your telescope, and so you can use that to measure a scattering delay. Which, being very simplistic, you can think of as kind of like the electron density squared integrated over the sight line. And then there's this dispersion, which is the electron column, which we mentioned, which is from the fact that the group velocity is less than the speed of light. Okay, so those are the 3 things that we can measure. I will finally, just as an aside, say that kind of weirdly in 2014, there were 3 techniques that people claimed could be used to measure the dispersion towards a non-transient source. So like you could just take a radio loud quasar and and measure the dispersion measure to it. And all of these used higher order statistics of the electric field. And they were all wrong or incorrect. The authors had made a mistake. There were actually people then trying to use these on observations, and some group was building an instrument to try to detect one of these statistics. And the major reason they were wrong, although this isn't true for all of them, was just a kind of a central limit theory. You can kind of make a central limit theorem argument that you can't detect any of these terms, and so that was done in this paper. Okay. 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 So going back to FRBs, so now we have data, and so this is an FRB that was discovered in the late 2018. It's a paper that came out in Science in late 2019. And the reason this FRB is interesting, so it's one of the first localized FRBs. In fact, it's the second FRB that is not a repeater that was localized to a galaxy. It was localized to this dwarf galaxy here. So this is where it's coming from. So redshift 0.5 dwarf galaxy. And then in the foreground, there's a big galaxy. This is a 10 to the 12.5 solar mass halo if you do abundance matching. So bigger than the Milky Way. At redshift 0.4, and it's offset by 30 kiloparsecs. A dark matter halo for this foreground galaxy, its dark matter halo should be something like 300 kiloparsecs. So we're going really deep within the halo of this foreground galaxy. Okay, so what can we do with that? So first, we're able to measure the rotation measure, and the rotation measure is small. It's actually consistent with being from the Milky Way. The uncertainty in the Milky Way rotation measure towards the sight line is comparable to the rotation measure that we measure. So we're able to put a bound on the magnetic field times the density going through. Remember, we're coming within 30 kiloparsecs of this galaxy, so that's kind of the characteristic scale. So going deep in this halo. And the bound on the parallel magnetic field is about a microgauss, which you might say, you know, I would say is not like a terribly interesting constraint, or I would have said. The equipartition magnetic field you would estimate is a couple, you know, maybe a little bit larger than that. There are some indications, or there's a controversial Nature paper that the circumgalactic medium, this gas within halos, may be highly magnetized from studies of magnesium-2 absorbers, and so there is some there are observational reasons to think that there could be a large magnetic field. But a couple of weeks after we published this paper, there was a group running cosmological MHD simulations that made this plot where they put our measurement, which we thought was an upper bound, but they're using it, or maybe you should think of this as an upper bound. These different curves are just different galaxies in their simulation. So this is the profile of the rotation measure. And usually I wouldn't think very much of these simulations. I mean, we don't know exactly, you know, what seeds cosmological magnetic fields, and so why should I trust cosmological MHD simulations? But what these simulations do tend to find is that there's, like, as long as they start off with a large enough seed field that they reach some attractor state that's just set by kind of equipartition or something like that. And so at least I think there's something interesting here. Okay, going on. So that was rotation measure. We're moving on to scattering. This slide has a lot on it, and I'm not gonna really go over it. But what I'm gonna say is that for this one burst, we're able to put a very what is the tightest constraint on multipath propagation, so that the scattering time is less than 40 microseconds. This is mostly because this burst is very narrow. So we're talking about the same FRB that's going through this foreground halo. So this is telling us about how, like, multipath it can be, like what the angle that the light rays can kind of bend going through this foreground halo. And so because this FRB is at such a far distance, you're sensitive to very small RMS density fluctuations in this foreground halo. And what we argue in this paper is that it's at least plausible with this. So the canonical way of interpreting scattering, especially in the ISM, is with Kolmogorov turbulence. or a Kolmogorov turbulent spectrum. We're really talking about scales that are magnetically dominated, and so we make an argument that it's at least plausible that like we see that we would detect a scattering delay at 40 microseconds if you just put in kind of characteristic scales that you would expect. So we think that our scattering constraint is saying something interesting about turbulence, but there's a lot of uncertainty. Maybe even more interesting than that is that there's another type of scattering, which is a refractive scattering. The turbulence is more diffractive. So there's this conjecture that we're talking about these diffuse halos, and we know that there's a lot of cold that are million-degree Kelvin. So this is the gas around this galaxy, or more than million-degree Kelvin. And these halos, the gas tends to cool to 10 to the 4 Kelvin. And so you tend to get a multi-phase medium where you have 10 to the 4 Kelvin gas, and maybe that 10 to the 4 Kelvin gas is what feeds the galaxy, and you have and 10 to the 6 Kelvin. And there's a conjecture that the 10 to the 4 Kelvin phase, as it's cooling, it tends to fragment to a scale that's set by the sound speed times the cooling time, and this gives you about a parsec scale. And so there's a conjecture that the CGM halos may be filled with parsec scale cloudlets that with large volume filling factors. And there's some evidence that this could be the case. And so one really interesting result of that, so Vedantam and Finney pointed out that if you take a parsec scale cloudlet, and these cloudlets are dense because they're compressed by this hotter atmosphere, so they're 100 times or more dense than the surrounding gas, that the focal length, especially if you add hundreds of these cloudlets, which is what you expect, can be comparable to cosmological distance. So this can give you a refractive scattering. And so we put some effort into driving formula for this. So we improved the kind of the formula in our paper, buried in a supplementary document. And I think we're for parsec scale, and I think there's some uncertainty in what the scale is, where I would say that our constraint on the volume filling fraction of these parsec scale clouds is maybe is almost probing the interesting space. But if the clouds are smaller than that, then we're quickly starting to rule out the kind of values that are motivated by the papers that are making this conjecture. So this is interesting, and I think this is something that's going to improve. Okay. Okay, so now now is the part of the talk that maybe is the most interesting. It's definitely the most nature-y part of the talk, that could be a negative description. But if there are questions, I am happy to take them. No? Okay. Okay, so we've done rotation measure, we've done scattering, and now we're doing the most important. We're doing the dispersion measure. Okay, so and this is kind of getting at what my original paper was mostly focused on, although it talked a bit about scattering. So imagine you have an FRB at some redshift, or an ensemble of FRBs at some redshift. Then their light is traveling through intervening stuff in the universe. And depending on whether they go through a voidier region in the universe, maybe this is a voidier region, and here I'm probably the probability of DM as a function of DM. Remember, DM is the dispersion measure. Then if I go through a voidy region of the universe, then this is going to contribute to the probability distribution at lower DM. If I go through a region that's maybe near a cluster of galaxies, then that's going to be a higher value for the dispersion measure. Okay. So so we're now thinking about the clumpiness of the universe and how the dispersion measure is like kind of how much do we expect it to fluctuate? What do we expect to drive these fluctuations? And so it turns out that it turns out that the fluctuations in the dispersion from sightline to sightline are what mostly drives it are how many halos, galactic-sized halos, my sightline goes through. In the picture where the gas associated with halos is kind of at a virial scale. With these dark matter halos, if it's out of order of virial scale, then the expectation is that whether I go through 5 10 to the 12 solar mass halos or 2 10 to the 12 solar mass halos within a virial radius is what's kind of setting the scatter. So just to make that a little bit more clear, here's the number of halos within a virial radius that are intersected out to a certain redshift. Let's say we do redshift 0.6, then maybe you're going through 1 or a little bit less than 1 10 to the 13 solar mass halo, but that sightline will go through a couple 10 to the 12 solar mass halos, 5 10 to the 11 solar mass halos, and it's the Poisson in this that sets the scatter, sets the width of the probability distribution in DM to that redshift. And there's a way of quantifying that also. You can do a halo model, and you can show that this is also the case for the cosmologists. So it's the diffuseness of the baryons around halos that sets the scatter in the dispersion measure. And so here, this is illustrating this again. So here I have 2 sightlines, and then these are my models for the gas distribution around galactic-sized dark matter halos. And so this is my clumpier case. Let's say the gas is closer to galaxies, and then this is the more diffuse case. There maybe it's a couple virial radii that has been pushed out by feedback. And so in the clumpier case, then I expect that some sightlines are going to hit some galactic-sized dark matter halos, and some might avoid them. And so we expect the probability distribution to be wider and to be more skewed. Whereas if I make the halos more diffuse, then the column now is lower because I've made my halo bigger. So the column across each individual halo is smaller, but then also I'm hitting more of them. Every sightline is hitting more of them, and so the Poisson fluctuations are smaller, and so I expect my probability distribution to be more Gaussian. Okay, and so you can quantify this. And so in this 2014 paper, we basically we just came up with simple models like top hat distribution around halos, assuming that the gas in some halos follows in NFW, and in lower mass halos, the gas is evacuated to large distance, and so we and others have improved these models, but but I think these models kind of give you a sense for what to expect. And the thing to expect is that the variance in dispersion measure, this is a redshift 1, but it's not so small. Like, so if I have a redshift 1 galaxy, FRB, then sometimes I might get 1400 as the dispersion measure, and sometimes I might get 700. So there are large fluctuations from intersecting these galaxies, and that's driving the fluctuations in the dispersion measure. That's from cosmological stuff and not from stuff intrinsic to the host galaxy. Okay, so now we're to a paper that applies this. So this is the first paper that really tries to infer things from the distribution of dispersion measures to FRBs. Let me just acknowledge that. So the lead author is JP Makar, and this paper came out, and then unfortunately a couple of weeks after this paper, or even a week after this paper came out, he passed away tragically. And in fact, so there's a push in the community to call this relationship that was in the paper the Makar relation. And what this plot shows is the dispersion measure as a function of redshift. So this is, in a sense, this is like the Hubble diagram for FRBs. Okay. And also, I'm going to note that all of this is, and the previous paper is as part of the Craft collaboration on ASKAP, which is really, in terms of localizing FRBs, has been leading the game for the last 2 years. And so many of the localizations are from this craft collaboration. Okay, so what is shown here? So this is dispersion measure, but it's the cosmic contribution to the dispersion measure. And what that means is just for visualization purposes, we've subtracted about 100 from the actual measured values because there's some contribution to the dispersion measure from the Milky Way, and there's some from the host galaxy. We can subtract the contribution from the ISM of the Milky Way pretty accurately. So that's also subtracted. So okay, so then, and so each of these are just different FRBs that have been detected. And just to give you a sense for the kind of the landscape, this is the famous repeater. This is a FRB that was detected by the Caltech group, and these are the ASKAP FRBs. And I think this is the last time I can ever show this plot because there are already a few localizations, many of them kind of right around redshift 0.2, and there's one at a very low redshift that's not useful for this exercise that makes it so that that this analysis is already getting a little bit outdated. And then the other thing to note is that this solid line is the expectation for if you had a homogeneous universe, this is what the dispersion measure redshift relation would be. And so you should note that, especially we've subtracted 100 from all of these, but they kind of trace this cosmic expectation. And then this solid or the shaded region is an estimate for the dispersion, the sightline to sightline variance or standard deviation in the dispersion measure. So the fact that sometimes you go through a denser region of the universe and sometimes a less dense region of the universe. Okay, and so I think the first thing that you take away from this type of plot is I don't see anything at like 1,000. And so at least for a lot of FRBs, the host galaxy contribution or the contribution intrinsic to the system it doesn't appear to be hugely dominant. Okay. Okay, but we want to do a little bit more. So I'm gonna, and we don't have very many points. We're dealing with 7 points. So I'm going to we're going to do an analysis that breaks this problem down into a very simple parameterization for different contributions to the dispersion. And so first, and actually there are members in the audience who came up with this PDF in a different context, but we found that this Murata, Escudé, Hanault, and Rees PDF actually fits really well the simulation probability distribution for DM to different redshift, partly because it has this nice skewness, and then it limits to Gaussian, and kind of in the limit when the standard deviation gets large, it becomes, or small, it becomes Gaussian, which is the kind of these limits that I was discussing earlier. And so and then we make a Euclidean argument. Like most of these FRBs are redshift less than 1/2. So we have a Euclidean argument that kind of the width of the standard deviation has to scale as redshift to the 1/2 times some parameter f. And so this reduces the intergalactic contribution to the sightline to sightline scatter to 1 parameter f. Then we don't know. Okay, the whole big issue, one big issue is that we don't know the intrinsic electron column from the host system, and so in the absence of information, you assume log normal. And so we have 2 parameters for log normal, a width and a mean. Okay, so there are 2 parameters here, 1 parameter here, and then this is a Nature paper, and so in order to get our most nature-y result, we also add the baryon density in the universe because we need to find the baryons. And so this is it. So this is this analysis, 4 parameters, and just as I would think of this as a consistency check. When we do this analysis, and part of this is just the fact that these points kind of fall along this curve, that like within order 1, is consistent with all of the baryons being there at redshift 0. More interesting are these other parameters, in my opinion, that are telling us that the parameters describing the log normal probability distribution of the host system are telling us that the host galaxy contribution is probably not terrible. And then this parameter F is our first constraint on how feedback has distributed gas around these halos. And that's what I'm going to focus on in the next slide. So this is, and I should say this is just the, this is a, so this is just, these are just the contours. This is here. This was a frequentist analysis. We also had a Bayesian analysis that of what values are preferred. Okay, so this is the feedback parameter, the parameter that's telling me how clumpy the gas is around dark matter, galactic mass dark matter halos. And so this is how what our analysis constrains this to be. So it's not very well constrained, but I will note that very small values of this parameter F are excluded where feedback is particularly efficient. And so I have like rough monikers for how you should interpret different values. And the reason for that, is like physically what is going on is that we have some of these really low dispersion measurements that like the systematic here can only bring you up. Like the host galaxy contribution can only bring you up. And so what low values mean is that that has to be from the intergalactic medium. I have to be going through a void region of the universe. And so these values are kind of pulling the saying that the amplitude of this gray region has to be sufficiently wide to kind of accommodate and this gray region is this feedback parameter, accommodate the low values. Okay, so we're starting to constrain feedback, and this is with 7 bursts. So there's only going to get better. And so this is the end of near the end of the talk. So we're going to go forward. There's going to be a lot of FRBs because there are a lot of facilities that are being built that can capture FRBs. The reason many of these facilities are built, and and in fact, I feel like maybe slightly responsible because I was on the other side for the cosmology side of and maybe guilty is not the right word. It's really good they're being built. Are being built to go after 21 centimeter intensity mapping. Many of them at lower redshift than reionization. So the world built up a lot of these arrays going after 21 centimeter to do intensity mapping. But it turned out that these arrays are really good for finding FRBs, and so they're all building backends to find FRBs. And so then in the future, there's going to be a lot of FRBs. So here is a review that came out in 2019 that plots how many FRBs there are as a function of time. And so I've extrapolated, and you can see, the future is bright. And here I'm also showing the number of localized FRBs. There was 1 in 2017, 2 in 2018. But then I realized I forgot to put on 2019, and 2019 CHIME detected 300 FRBs, and then we've localized about 10 in 2019. And so if I extrapolate now, it's even looking better. So there's going to be a lot of FRBs. In fact, if you go to an FRB conference, there will be people talking about localizing 10 million FRBs or 100 million and doing cosmology. That is not the cosmology that I was referring to in the last part of my abstract, but that I'm not going to discuss. But yeah. All right. Okay, and then what does the science look like? So the science does not look like the science that I described before, where I parameterize everything and I try to fit the PDF for the PDF of the intervening DM. And what the science instead is going to look like is you're going to have a bunch of FRBs, and you're going to have foreground galaxies, and you're going to then stack the foreground galaxies, the FRBs in the relation to different foreground galaxies of different classes as a function of impact parameter. And this is gonna in an unbiased way. That's unbiased by the host galaxy contribution to the dispersion, because the host galaxy contribution doesn't care what the impact parameter is to a foreground galexy. And so from that stacking, that's how we're going to measure the profile of gas around galactic mass halos. And the estimates are that you need at least 100 localized FRBs to be able to do this. But once you have a localized FRB, you get for free the foreground galaxies, and so then you can do this stacking analysis. So the future is stacking. And then maybe I'm just going to shout out to CMB, which I think of as a major competitor for this. The only other thing that's really sensitive to all the gas, to the electrons, is the kinetic SZ effect. And so the future CMB is also going to do this type of stacking, but they'll be stacking the kinetic SZ anisotropies in a kind of a coherent way. So the forecasts are that they can do this for bigger halos than we think FRBs can be used to do this. This is partly because of what redshift samples we have for galaxies. You need the redshifts of the galaxies to a lot of galaxies to really do this. And just a shout out, ACT did this recently for LRGs where we have a lot of galaxies, and this is already putting constraints on 2 × 10⁻³ solar mass halos that are really interesting. And the models they have models that can I'm not going to get into this plot, but in a lot of detail. But the shaded region is what this kinetic SZ stacking is saying for the electron density profile. Kind of at pretty large radii, because the beam for these telescopes is large, so they're not able to look at the inner parts of halos. And then they're also able to do this for the thermal SZ, which is another anisotropy. And the models that match one, and these are from cosmological hydrodynamic simulations, are really discrepant actually for their other measurements. So there's some interesting thing going on, that the models are not even close to reproducing the observed profiles of the using the stacking in these anisotropies. Okay, so that's it. So we used FRB 181112 to do the first diffuse baryon science with FRBs. We find that the magnetic field is sub-equipartition, which is weirdly consistent with recent cosmological MHD simulations, and is lower than some inferences towards magnesium-2 absorbers. We have a really tight limit on the scattering, which constrains the level of turbulence in these halos, and it also constrains these parsec scale mist thermal instability models. And then for our signature analysis, we took 7 bursts. We found the baryons, and this is the kind of the first measurement of this Makar relation. But I think what you should take from this, what are the most interesting takeaways, is that the host galaxy contribution doesn't look, for at least the FRBs that have been localized so far, to be humongous. Which makes it so that, for example, when we do the stacking as a function of impact parameter, that's going to be a noise. So the noise in that stacking is less than it would be if each host galaxy contributed 1,000 parsec centimeter cubed. And then I think the constraints on the density profiles of the circumgalactic medium are going to get interesting faster than you think, because there are a lot of instruments that are coming online that can do this, and there are also outrigger and telescopes that are being installed to localize, for example, these 300 time bursts. Eventually they'll have long enough baselines where they can say, oh, it's in that galaxy. And so just finally, these constraints are relevant for the intergalactic medium, for galaxy formation, and they are relevant for precision cosmology. Thank you.
Thank you, Matt. That was intriguing.